Okay, let's start. I wanted to continue on the theme of power management, which we've been doing since past two lectures. We saw kind of a couple of very broad sort of techniques, shutting things down dynamically based upon when things are idle, and we kind of talked about what might kind of this notion of break-even point and how you can select kind of judiciously um, the time or the threshold after which a system should go to idle, and we kind of saw that there are also kind of stochastic techniques which could potentially do better, and also kind of the concept of scaling. And then sort of we briefly towards the end talked about other kinds of things which one can do, and essentially they kind of boil down to don't waste energy. And I gave the example of how handling of timers was something that was done rather inefficiently in a lot of operating systems. So essentially, when the system went into the idle loop, uh, timers would keep triggering, and that would, guys, can we? You're disturbing. Okay. Um, so, uh, kind of in the idle loop, instead of timers coming continuously while just waking things up, one could be smart about it, and all the major operating systems kind of do some variants of that. So, for example, Linux introduced this notion of tickless kernel, where basically instead of the timers still coming periodically while idle, it would now arrange for it to come at the next event, which could be far enough out, and that basically gave opportunities for longer sleep times and fewer interrupt handling. And similar kind of concepts in other OSs, so like in Mac OS X and Windows, they have this notion of coalescing timers. So idea being when the timers are generated in response to a call like a sleep, they tend to be kind of all over at arbitrary point in the real number line, so to say. So what if we were to coalesce them so that they um, nearby timers are consolidated into a single wake-up call, and so you kind of relax a little bit on the accuracy of the timer, which is acceptable for vast majority of workload that standard computers face, but it increases the opportunity for sleep. So kind of bring them together, and this was kind of the example of how in Mac OS X kind of you ending up with more opportunities for sleep. So these are obviously orthogonal. You can have tickless together with coalescing of the timer, but they all sort of are towards this purpose of doing things and sort of maximizing the sleep time. In context of real-time system, one can play kind of the same game that the scheduling techniques tend to be um, work conserving, namely if the CPU is idle and something is ready to run, they would run it. But instead of that, you could go towards non-work conserving schedulers, where the idea is we may deliberately choose to leave things idle, either because we are confident we can still meet the deadline, or somehow we know about the future arrival patterns, and that can again result in better optimization. So, for example, in this particular case, if you look at the tasks out here, then by just shifting it out, we can still meet the deadline, but increase kind of the idle time of sleep time opportunity. And I guess more recently, what's been happening is there is notion that we could have energy adaptivity and not simply kind of save energy, but rather scale gracefully with workload. So we saw DVFS as one example of it, but with emergence of processors which have multiple heterogeneous cores. So the idea is that you have lots of processor cores on a chip. They have the same instruction set architecture, so they can run, each can run the program, but they have different performance power curves. So a good example is some of these, like the Exynos chip out of Samsung, which has 8 cores. 4 of them are big cores, big ARM cores. 4 of them are small ARM cores. Any program can run on either the big core or the small core, but if you were to look at the power versus performance curve, they are different. So kind of the idea is that you want kind of the right mix of processing resources depending upon what your current workload is. So that's another form of adaptivity. Instead of changing voltage in frequency, you kind of also have this architectural heterogeneity that you can exploit. So in the next slide set, which I'd handed out last time around, we'll go into power management in Linux in more depth. But the other thing I also wanted to bring out is that there's a lot of attention that is also being paid by computer manufacturers now on what they call as life cycle energy efficiency. And the idea out here is that you kind of have energy consumed in the production phase. There is energy which is consumed during the lifetime of the product. So this is what power management and all handles. And then also there is energy spent in the disposal. And you could have a product, for example, you could have a product which is extremely energy efficient in its runtime phase, but makes use of production techniques or materials which are extremely energy hungry in the manufacturing phase, and then kind of one could make the case that from an overall societal perspective and viewed in a long-term basis, that's probably not a good choice. That's not always a sole consideration. Sometimes runtime power management is important for other reasons. For example, energy being consumed at the right place. Like, for example, there may be a lot of energy in energy may be cheap in one country and expensive in a different country, and therefore you want to kind of change that balance also. So it's a complicated story, but you would see most major manufacturers kind of now do worry about it. So it's a life cycle aspect also. And what do you think is driving them towards this life cycle consideration? Is it simply they are good companies at heart and therefore want to worry about the production energy cost, or there's something else which affects their bottom line, or which is, huh? Okay, possibly. I mean, it's possible that that things are more power efficient and also cheap, more energy efficient to manufacture. Although I would say probably not. It might actually be the other way around, which is costlier to manufacture things which are more power efficient, perhaps. Any of you heard of this notion of carbon credits? Carbon credit?
I know you can buy them to offset the carbon that you use.
Yeah, so kind of the idea, exactly. So kind of the idea is that EU and California and some other places, not rest of the US, have begun to create this notion of an energy marketplace where essentially you can trade your so carbon credit basically refers to how much carbon you emitted in course of your normal business operation, how much carbon a company emitted, and you can trade it on the market. So for example, a company which is less efficient in its manufacturing processes can buy it from one which is more efficient, and companies can kind of make this choice about, like, you know, we can invest in more costlier but more energy efficient processes and then sell those credits, or you can even kind of move these credits across from like one country to another, in EU, for example. So there is a rational economic reason also because of which they have begun to worry about these. So there are both these aspects. One is feel good aspect, particularly because there are organizations that now rate the product based upon their manufacturing and disposability, but also there is this economic factor also which is kind of driving this. So the overall life cycle context also has kind of become important, and it's a complicated kind of story, but there are tools, and also this package called Umberto, for example, where let's say you're designing an electronic product, you can go there, you can specify the kind of materials and all you're using and all, and it kind of gives you a first cut sense of what your manufacturing energy footprint is going to be and what the disposal footprint is going to be. Okay, you kind of give a massive spreadsheet, and also this is the kind of stuff which manufacturers and all kind of use basically. So just to give you an example, production in China of a desktop PC takes 2.4 gigajoules, and in 1 year it consumes 0.8 gigajoules. Okay, so if you are like me, replacing your laptop every year, actually bulk of my energy usage is actually in the manufacturing of the laptop, not okay, so desktop PC, as opposed to what I'm kind of spend what I'm using during the year. And let's say I take some energy efficiency measure and reduce this thing by, let's say, I don't know, optimistically 30% or something. That's a tiny amount of the overall footprint that thing consumes. So what that also says is that actually one of the more effective energy measures from this life cycle perspective would be the ability to sort of modularized systems so that you can incrementally upgrade them as opposed to kind of having to discard. That's one perspective. Another perspective is that perhaps these things can be recycled in other ways, like, for example, I don't know, my old computers get used by my students, okay, but kidding aside, but you could, there's a whole industry out there where they take first world computers, cell phones and all, and then use them in poorer countries and all. So that's another form of extending the lifetime, and one could argue that mitigating kind of the life cycle footprint. In any case, and part of the reason this becomes an issue also is increasingly is that our product life cycles have sort of shortened quite a bit, since it used to be you would upgrade every 5 to 10 years, but now rare would be that one would hang on to things like mobile phones and all for anywhere close to that long. In fact, they're not even designed to be that long lasting. So kind of these kind of issues have sort of become quite important as well. There is this whole culture of eco-labeling of computers, so Energy Star. I'm sure you have seen these things in appliances and all. This is basically in the US, it's kind of a standardized way of comparing energy efficiency of different types of products, computers inclusive. It defines various kind of like hibernation, different kind of sleep modes and all. It sort of rates on that basis whether a device or a product have these kind of things or not also. So very systematic stuff. And likewise, in other countries, EU in particular has similar stuff, and there are standards also about kind of covering the production and the disposability aspects also. So just want to leave you with that thought that it's not simply about what is happening while the system is, and we already saw that it's not simply about when the system is actively doing something, it's also about when the system is idle, that was doing nothing very well. But these numbers also suggest that it's also about what happens before and after also. It's not sort of while the system is powered up. But that's sort of a little bit tangential to what my goal is with this course, so we're not going to go deeper into that. So next topic I wanted to go into was looking at power management very concretely in context of Linux. The choice of Linux partly being because there's a lot more information about it out there, but partly also it's sort of the embedded OS of choice now for so many products. Okay, it's used in network products, phones, I mean all sorts of devices. So ideas in Linux in some senses have a lot more kind of impact in terms of device, in terms of sheer numbers. So the holy grail of power management basically is that we should use, so now again back to focusing just on kind of runtime, so not production, not disposal. So holy grail is really to use energy only as much as is needed to get me sufficient performance. Okay, so it's a very loosely defined set of things because oftentimes we don't even know what is sufficient performance. Now, what software can do in this thing, as we saw in a more abstract way earlier, is that it can figure out how much performance is needed, and so like how much throughput, how much latency, and so on and so forth. And then what it can do is it can arrange to operate the hardware in a fashion that delivers that level of performance while optimizing for energy, power, or some such other metric, and perhaps do so in a holistic fashion, that is not just energy which is spent in actual computing, but also to cool the stuff and taking into account losses and stuff like that. So in this whole thing, the main role typically gets played by the operating system kernel. So because it has the ability to turn on and off things, because it manages all the resources, so it has it controls those knobs that let you shut things down, change voltage, so on and so forth. Also, it has the ability to wake things up, interact with applications. It also is uniquely well positioned to observe processes and all and figure out what their cost is going to be as an application periodic, all those sort of things. So that's one thing. It can turn things off. It can also sort of estimate things, what is happening and what the application wants, perhaps either through direct API calls. The application tells it, I need this deadline or whatever, or the kernel observes and sort of makes some inferences about it. So to make this happen in a actual operating system, there's going to be a bunch of building blocks. So there have to be some concept of ability to suspend and resume the device, so like the user going away kind of thing. So these are more longer term type of things. CPU being idle, that's potentially another building block. So this is now smaller time scale. CPU idle, can I, or other parts of the system idle, can I do something about it? Frequency and voltage scaling, and of course applications can assist in this process as well. So in case of Linux, I think the way power management got organized in part kind of is just reflective of the way sort of history evolved and people implemented things, and also it's not necessarily what, if you want to now design from scratch, you would necessarily do, but it is the way it is. So very broadly, there's a distinction made between system-wide power management. So in this case, we are talking about the global power states of the system. So the entire system hibernating or going to sleep, you're shutting down the screen of your laptop, those kind of things. And kind of the idea is that the user or the user space decides which energy saving state to go and when. So these are kind of very the longer time scale type of power management that is happening. And then there is a short-term or a more immediate type power management, which is referred to as runtime power management. And the idea out here is during the course of the execution of an application, different subsystems may get needed or go idle, and somehow kind of deciding their state, shutting them down, scaling their frequency, those kind of things. So system-wide power management and runtime power management. And you could imagine that they really don't need to be separate in the sense that it's system and runtime scale, and you could imagine that if we can have just everything in a runtime power management and we sort of deal with that. But that's not sort of currently it is. So suspend and resume. This basically, as I said, refers to longer time scale stuff. Okay, so within the kernel there is a infrastructure for supporting this notion. So device platform can go into different levels of, so it can be active or go to different degrees of being unavailable. So at the within the kernel they have support for these things, various sort of API calls and all. And then now, as you might imagine, this is sort of a complicated thing because you cannot, the OS cannot simply say, okay, suspend, sort of just go into it. There is a whole bunch of peripheral subsystems and all which also have to coordinate in this process. So the device drivers, for example, now also have hooks in them for suspending and resuming. So kind of the idea is before you go to suspend, you have to tell each device driver you have to suspend, only then kind of system suspends. And then likewise, when you're coming out of it, the whole process has to be kind of repeated. So as you might imagine also, this therefore obviously is also tends to be board specific in the sense that it's not something simply Intel can decide. It kind of is depending upon a cooperation of a whole bunch of things which are on the system. And then you also have to deal with kind of battery operated systems and additional stuff. So as insofar as the kernel is concerned, there is CPU specific code out there which kind of deals with CPU states. And again, kind of we largely have two dominant CPUs in the space, the ARM based stuff and Intel based stuff, and they are different. So Intel defines for their processors a whole bunch of states and all, not all of which are available in ARM. So there are variations there as well. So the process starts out by some way in which suspension is triggered, and so it could be shutting, like whatever, selecting the sleep from the menu, or shutting the lid, or sometimes there may be some special button to press to put the things in sleep. But the idea is at the end of it, somewhere in the kernel, this function which starts the whole process gets called, which then kind of goes out to every device driver, have them suspend, and then gradually kind of the process proceeds. You could trigger this thing from user space in Linux. So for example, there is this system file, part of the system by street called syspower state, and you can write the state you want to go to by essentially writing to that. And there are also dedicated sort of programs, and since there are different kinds of suspend, again, depending upon the platform, so there are many different options available. So for example, in old days, pretty much what used to have was very, very common that for longer time sleep, you would save the state on the disk. Nowadays, with DRAMs being able to retain state for long periods of time because it can lower their voltage, so suspend to RAM has become very common. So there are all these variants: suspend to disk, suspend to RAM. I think suspend to disk, at least on the Mac side of things, has entirely disappeared. On the PC side, we still kind of see it, but suspend to RAM is much more common now. So different types of suspend, and like I said, something in the user level is going to trigger it, an application, the user himself, and all. What the system allows for is a whole bunch of degrees of deeper and deeper suspension, if you may. They're given different names and all, but kind of the idea is that you gradually transition to it. Hibernate is kind of the deepest one. Things go into the hard drive, and you kind of recover out of that. So there are complicated sort of control flow in the process, but without walking you through these, the gist of them is that I need to first make sure that each device goes to sleep, and then the CPU goes to sleep, and then the reverse direction, you have to, upon CPU wake up, you have to wake up each one of the device. So, so essentially, a bunch of these states with different degrees of power saving, controlled by something in the user space, mechanical action or running a program or something like that, or perhaps even a timer kind of decides that. This notion is available in modified form in other cases also. So Android, which builds upon Linux, has this notion of Wakelocks. And the way Wakelocks work is that by default, if the OS is in the idle loop, that is, there is nothing to do, then it will go to suspend. But applications can explicitly request the OS not to put them to sleep, or not to put certain subsystems into sleep, by taking out what is called as Wakelocks. So Wakelocks essentially prevent suspend. So so instead of actively requesting suspend, the idea is it will suspend unless you tell it not to. So an app can say, I'm in background, but I need the CPU, so it will put the wake lock on the CPU. And then the kernel will make sure it doesn't go to sleep. Things don't always work as intended, and I think these policies keep changing. So for example, it seems like wake locks do not work properly on the new watches which have come out from running Android. So like there are a bunch of them out there from Motorola and LG and all. They run Android for all practical purposes. They're like a little Android device running the very same OS, but because energy requirements are so severe there, at least what it seems is that even if you take the wake lock, the system still goes to sleep. Okay, so I guess there the notion is that the only thing which keeps things up are explicit user actions, pressing a button, or the phone trying to contact the device and all. So it's a choice that, for perhaps for battery reasons, Google seems to So what is happening in this space is hibernation, as I mentioned, is a dying thing. Uh, it's uh, it's its utility. So firstly, it was uh, never really supported on the ARM side of things, but even on the Intel side of things, now there are other technologies which are kind of replacing them. The other thing is that many platforms now do not like to be offline. What I mean by that is this notion that you can go into a state where the only things that will get you out of that state are a user action or a timer, which is how Hibernate and PCs work. You could have the user press a key or press a button or something like that, or the other alternative was that you could set a timer which would cause a wake up to happen at, let's say, 7 a.m. in the morning or something like that. In many platforms now it doesn't make sense because we often use our devices in ways where they need to have a network presence. We'll see this thing a lot later also, but essentially, I don't know, if you use your laptop for Skype calls and all, something needs to wake it up. I mean, your other alternative is to keep it up all the time. So you want some variant of going to sleep but still listening. Okay, sort of sounds oxymoronic, but a lot of our applications are like that because we are on the network, things need to contact us. In a very simple case on a phone, of course, we want to receive phone calls, but a lot of our internet applications and all are of that nature, messages coming in, things like that. So this entire platform being truly offline is not something which modern usage supports. But the other part also is it's not necessary either. So like I mentioned, we can maintain the state of the memory state for long periods of time. So DRAM can now last for a long, long time. It didn't used to be. So originally, when things like hibernation happened, kind of technology was very, very different. But now things have changed quite a bit. So complementing the whole platform power management is the runtime power management. So this specifically is referring to shorter time scale decisions about the state of the system. So you could temporarily put specific things into sleep, like for example, maybe like while I'm giving this lecture, the display needs to be up and all, but not the hard drive if there were to be a hard drive, so it can be spun down. Those kind of things can happen. So parts of the hardware system can be put to sleep. There are extreme cases also, like even the display and all. You could imagine that if it's a static image, the graphics subsystem can kind of, the GPU can go to sleep, just the frame buffer is being refreshed, things like that. So that's the second type of support that is needed, and that's this runtime thing. So there are several different frameworks within Linux. It's a little bit of a hodgepodge currently, but what it does is it separates out the two broad strategies that we talked about, shutting down the CPU and scaling the CPU. So corresponding to it, there are two separate frameworks, software structures within the operating system. So there's one which is called CPU idle, and essentially what it does is it arranges for a processor, some of the processor core, some subset of the core, potentially to go into a low power state. So the idea out there is, again, modern CPUs have many cores. Not all of them may be needed by us. So what we can do is to put some subset of them into a low power state and use the remaining one, basically. So and when you do it, which core you do it to, not all cores may be identical. There are all those kind of issues come into play. Depends upon what is happening to the workload. So for example, if the load on the system is less, really tiny, maybe you just keep one of the tiny cores up, put everything else to sleep. Now, there are costs associated with this process. What do you think they might be? So like this decision of putting cores to sleep, waking them up. What do you think might be the cost besides kind of just obviously the act of actual waking up the core? No, that affects the decision, but like cost in terms of when I decide to shut down a core or when I decide to wake up a core, what all would I need to do? Transferring the state from one core to another, right? Because the way Linux works is it distributes the task to the cores, and then there is a scheduler for each core which is managing it. Okay, so it's not like you keep moving the tasks around. So when you do make a deliberate decision to shut a core down, then those tasks need to be redistributed. That means the state needs to be transferred. And the reverse direction, when you're making the decision to activate a core, then of course it's with the intent of running something, so you're going to again redistribute the task. So there is this sort of global sort of work that would need to happen for the strategy to work. These operating systems do not are not something where they're operating from a single work queue where one moment the task may be running here and the next moment the task runs on a different core and the next time it is reactivated it runs on a third core. It doesn't work like that. They are pinned to specific cores in case of Linux, and therefore as you change the set of cores that are available to you, you have to kind of do this reshuffling of the tasks basically. So so that's what CPU idle has to do. Then the other part is CPU performance scaling. So the idea now is, so first part is selecting which cores are up, and the second one is saying, and by the way, what performance level are these cores operating at, namely what frequency and voltage. So this again, as you might imagine, would depend upon the load, and of course, it kind of, as you imagine, these two really cannot be independent, truly, even though that's what they are. So so this framework is called CPU Freq, or at least the older version of it, but there are also some newer variants into this bonding. But basically what these guys are doing is they're basically combining, these are basically moving a particular core across these different operating points. And there are usually limitations on it, like for example, in some cases, it could be that each core you can change its voltage and frequency independently. Oftentimes, it could be all cores on a given package can operate at a frequency and voltage, but different packages, that is, different sockets, they can be different. Okay, so there are constraints which come into play. The C states of a CPU, this is an Intel terminology which is also used in the AC power management framework that we had before. So C states refer to the broad states of a CPU or a system in terms of active, shutdown, sleep, hibernate, those kind of things. And then P states, power states, refer to while the CPU is active, its different performance states. So if you look at the overall system, or each subsystem is going to have a bunch of C states. One of them is going to be the active state, and within that active state, there would be a whole bunch of performance states. So in case of CPU, it might be frequency, but for hard drive, it might be, I don't know, the spin speed. For display, it might be the resolution. Like for example, some of the Apple laptops had dual GPUs, and it would switch between a low power, low performance, and a high power, high performance GPU automatically. Okay, so game playing, it would kind of switch to the high performance, high frame rate. So those kind of things can exist. These are treated as separate, but obviously a proper design of them would make, these are coupled. I mean, they're both ultimately being decided by the workload that we have to do. So right now these are often in conflict, but nevertheless these are designed sort of in a reasonably nice fashion, and a lot of it is actually accessible. So if you have a Linux machine, you can easily play with it. All these things like what cores are active, where, what frequency they are running in and all, is all visible through that very same sys file system or proc file system, depending upon your Linux release. And you can write to it and control stuff. So you can easily disable or fix the frequency of a particular core, things like that. These are all like, unlike, let's say, Mac or Windows, where these things exist, but they're kind of hidden. in case of Linux, all the system details are visible to you. So playing around is actually pretty easy. So these frameworks are separate, but conceptually, they or ideally they should have been. So what kind of problems do you think would come from these two things being separate? What do you think gets the priority? Okay, they are separate. So what gets the priority? Like how is it? What core am I running on? Like what cores are active, or like what speeds they are? Like what do you think?
What has priority for what's
From the OS perspective, right? I mean, OS has now these two subsystems, both of which are striving to save power. One controls what cores are running, one controls what speed a core is running at.
For fine grain control, we might change the speed, but for coarse grain control, we might turn off cores.
Yeah, so global control is done by the CPU idle. Okay, so it makes its decision first, and then CPU frequency basically makes its decisions around that choice point until there is a significant change in the load, in which case CPU idle again kind of takes over. Okay, and then of course, like I said, through user program and all, you can also influence the CPU idle. There is a notion of governors in these systems. So these are user space entities where the policy gets decided. So it's kind of a nice framework. They separated out the mechanism from the policy. Okay, so that is how do you shut things down and all that the OS provides, and then they give you kind of a plug-in architecture, which they call as governor. Governor is where the policy gets decided, and you can write your own if you want. There are of course a bunch of canned ones, but more importantly, it makes it easy to play with power management in Linux. Okay, so and because these things run on the user space. So part of this thing also is saving power in the idle loop. It kind of goes back to doing nothing very well, and we saw the tickless timer and all were kind of aiming at that. So idle loop is pretty crucial because in many systems a lot of time is devoted out there. So this is what the OS does when there is nothing left to run. And deep down there will be such a thing, okay? Because what's going to happen there is no active process on the queue. There might be some events like timers and all, and of course there might be external events coming in. Those are only two things that can then dictate next what is happening. So usually the way these things then get implemented is you go into some sort of special power saving mode, run some special instruction, halt or something like that, and then arrange to be woken up. And this is where I mentioned that old Linux kernel were tick based. So there was a timer hardware which was supplying an interrupt every sometime t, and will wake up on that. But now what happens is that these things are tickless, that you when you enter into the situation, you reprogram that timer so that it wakes you up when there is actually an event to be done. So there are a bunch of advancements happened over the years. Okay, there are also some kind of dynamic ticks and all, but kind of the main idea is that the CPU idle infrastructure is the one kind of managing this thing. So the way this code gets organized is that there is platforms. So there's a general framework, and it has a platform-specific driver. So that's the lower layer, which is how this framework interfaces with the specific capabilities of your board. So your hardware has to define how to put it into sleep, what the knobs are and all, because it might be a different set of peripherals and all that exist. And the other part is there is a platform-independent set of governors, which is where the policy gets decided. So for example, there are governors called ladder and menu. So in case of, let's see if I have, unfortunately I don't have a slide on that, but the way these things work is, in case of ladder, what it does is it keeps messing with the parameters of its policy in kind of an incremental fashion. And so it's kind of a greedy kind of an approach. What menu does is, so kind of the idea is you're trying to decide when to shut down, which state to shut down to, okay? In case of menu, what it does is it kind of looks at the recent history and based upon that decides which sleep state to go to, okay? This infrastructure is not necessarily supported by all the ARM CPUs. So a lot of things in Linux, because of its heritage, happened around the Intel architecture. So ARM is a more recent entrant. So if you play with like BeagleBone or Raspberry Pi or things like that, not all of these things are necessarily kind of supported. So conceptually, then the CPU idle structure looks like the following. There is a main framework. There are these drivers which basically let this framework actually control the states of your platform. And then these are the governors which are running in the user space, which is when the policy gets decided. There are, like I said, common ones, but if you read some of the papers and all in the space, you could write new types of governors. And then finally, a lot of these capabilities are exposed through the sys file system so that you can actually control it through scripts and stuff like that. So you can affect the state of cores. So the ladder governor, what it does is, these governors, what they do is that as when you enter the idle state, it kind of has to now decide which specific state or set of states in the platform you should transition to. And then it tells the CPU idle infrastructure do that, which then will contact the driver to make that thing happen. So this I already covered. Okay. Now there are other complications which also come into play in this. So imagine again there are multiple cores. Question comes up, where do the interrupts go? So you have a chip, multiple cores, the interrupt line, where does that interrupt go? Well, these multi-core chips tend to have some sort of interrupt routing infrastructure. So kind of the idea is that you can configure the hardware to route specific interrupt lines to specific cores, because and this gets needed because if you decide to put a core, if you decide to take a core out of action, then there are two possible ways of thinking about it. One is I put it to sleep, but I still want it to be woken up when the interrupt comes, so it still needs to serve the interrupt. But the other one is I truly want to take it out of service. In that case, I want to transfer not simply its tasks, but also its interrupt handling, interrupt handlers onto one of the other cores. So that's what this does. It's a piece of hardware sitting on the chip, and it basically arranges for interrupts to be routed to the core as defined by the OS. So common possibilities that it does are things like route all interrupts to a logical CPU number 0. So there is some particular CPU, let's say, if it's a symmetric core chip, all cores are identical, you just designate one to be CPU 0. In other cases, if you have heterogeneous thing, again, you cannot make some sort of a choice. The idea is that you route all interrupts to that core. Another possibility is you broadcast, and then in software decide who's going to be kind of handling that. So part of power management infrastructure then also is to control this hardware so that we can redirect interrupts to the right place. Because if you don't do that, then a lot of the benefits of power management sort of go away. So certain interrupts are more important, like when a network packet arrives, those kind of things, whereas other interrupts like keyboard and all might be less so. So what it does is it keeps an eye on what's the activity rate, how many interrupts are coming, arranges for them to be balanced. You do not want a single core to be burdened with all the interrupts. You want to distribute them evenly, but at the same time, when a core is being taken out of service, then you need to reallocate its interrupt to another core. So all this kind of magic also has to be done, and it's coupled with what is happening on the CPU idle framework. So the remaining stuff then is how do we control the performance? So this is where frequency and voltage scaling come into play, but the P states, the power states, could take other form also. Like I said, for disk, it could be the disk speed. For GPU, it could be refresh rate or some other thing like that. For other parts of your system, for network, maybe it could be data rates that you are sustaining. So it could be a whole bunch of different possibilities. So the infrastructure, in case of CPU, this infrastructure is called CPU stack. And idea out here is that just like we had governors here, this ladder and menu, in case of shutdown, there are similar governors out here, but their task is to control the speed. So there is a governor called performance, and it basically always selects the maximum frequency. There is a governor called power save, which always selects the minimum frequency. There is a governor called on demand. What it does is it measures the CPU performance and then uses certain thresholds to take the frequency. There is a governor called conservative. What it does is it gradually ramps up the CPU frequency as the load increases, but then resets it back. And then finally, you can always do it through user space. So again, through the sys file system, there are files to which you can write the frequencies that you want specific cores to operate at and pin them at that frequency. So you can write your own kind of a script, in effect, controlling the performance of the system. So for each core, you can kind of do it. So it's pretty flexible way for making things work out. So particularly on like if you have one of these octa-core Samsung phones or something like that, you can play pretty cool stuff like make your entire phone run on a small single arm or kind of bring up all the 8 cores. Sometimes hardware places limitations on what combinations of cores can be up or not up, but other than that, this framework provides complete control. So again, kind of if you are porting Linux to kind of a different platform, then you'll have to write the low-level driver functions, which for your CPU let you interface with this CPU frequency infrastructure. So in some senses, porting Linux to a board that you have designed around a chip really kind of boils down to writing these low-level drivers, which let the CPU idle framework to shut things down and CPU frequency framework to control these performance norms. And so that's so now these frameworks that I described, they have been around for maybe the past 8-9 years. Okay, so I think the early versions of these things had started appearing maybe 2005-6 kind of time frame. So obviously, technology has changed quite a bit since then, and a lot of multi-core weren't that common. Certainly, Android phones weren't there, so a lot of things have come along since then. But now people are also kind of actively talking about kind of revisiting these frameworks from a more cleaner design kind of perspective. So there is something called Power Management Quality of Service Framework, which Intel introduced. And kind of the idea now is that applications can specify a whole bunch of things like how much latency they need for DMA, and how much latency they need for networking, so on and so forth. And then the OS takes these hints, puts them together, does the power management based upon that. I think what's also happening in this space is that what used to be, again, kind of Intel-only kind of thing is a much more complicated story at this stage. Certainly ARM and Intel, but you also have like MIPS and a bunch of other platforms which also run Linux. So power management is sort of a fragmented story. So additional stuff, boards where you have these capabilities of changing frequency and changing voltage and all. typically would come with their own specific hardware implementation. The voltage changing is not something that happens within the CPU. It is something which the board vendor puts regulator, which power supply, which has this capability. So all that framework also needs to be provided. So some thoughts on where things are headed. So multiple CPU packages, and within a package, multiple CPU cores. That's what the landscape is. So even you may have a single chip with a bunch of cores, and then oftentimes on the same board you have multiple chips. And they all present different constraints on what states you could be at and what frequencies could be at. So for example, early version of Samsung devices, they had these constraints like you could be, they had 8 cores which were 4 pairs. Each pair was a tiny core and a big core, but the constraint was that you cannot have both cores in a pair active. So you could shut down an entire pair, or you can activate a pair, but within that pair you have to select one core. Okay, you cannot have. So these were kind of constraints. Some of them were coming from hardware reasons. Some of them were just limitations in the software. One direction that people have begun to take now is power management aware scheduling. So ultimately, all of these things about putting core to sleep, changing its frequency and all, these are all dancing around kind of the very basic issue, which is this is about scheduling CPU, deciding when to put it to sleep, what voltage to run at and all. So those of you who are in 202A, we saw scheduling for real time and all, and these things from the academic side at this stage exist, run on system and all, but their adoption on platform like Linux, I mean, many years behind. There's a gap between kind of the academic results and what kind of the production systems are. But now, again, the push from Intel and all that seems to be changing. So the current thinking at this stage is that sooner or later we'll see the adoption of largely known ideas. So essentially, your scheduler becomes the central point. It decides, among other things, when to activate things, when to shut it down. Everything just becomes a scheduling problem. And you do not have this separate hibernation, sleep, CPU idle framework. You do not have this separate notion of I'm going to change the frequency, because right now what happens is when you're changing the frequency and all, you are doing it based upon these course policies, and therefore very little ability to control what is happening in terms of the deadlines and all. So Linux, even though we normally do not think of it as a real-time system, has a component. Every recent Linux release has a component which is a real-time system. It has real-time threads, where it actually seeks to make you guarantees. They work along the lines of those preemptive schedulers that we kind of discussed in 202A. So all that basic framework is there. But then the CPU frec and CPU idle come from the side, and they basically start messing with that. And the reason is because scheduling is separate from this power management. And the change that is happening is that move towards making scheduling power aware, and then removing these kind of frameworks which are tagged along to that. So that's the direction which is happening, and in the process we would see performance scaling and idle state management all kind of get combined into one. So that brings the question, how might that happen? So I mentioned Linux has a real-time part, and then there is a rest of Linux. The rest of these non-real-time stuff then gets managed by something called a CFS scheduler. And the way conceptually it works is the following, that it keeps an accounting for every task, how much time it has consumed. Okay, so it's sort of a nanosecond type counter which it kind of maintains. And for each task, that counter is maintained. And kind of the idea is that how much time a task has consumed gets to dictate whether what priority we will execute it. So it's essentially is trying to be fair, which is what makes sense for a general purpose thing. You do not want to starve a task out. There's no real-time goal. So it uses a particular data structure which is called red-black trees. But the main thing out here is that the leftmost tasks out here are the one which have consumed the least amount of execution time and therefore have the highest need to be prioritized for execution. So choosing a task is order one. You can pick it up. Reinserting a task. So the idea is after you selected a task, you ran it for some time, its virtual execution time went up. You are now going to reinsert it back at the right place, and that takes order log n. Okay, you need both of these things to be efficient. So this particular data structure is doing that. What do you think are the disadvantages of this strategy? That I'm always going to give time to the task which has consumed, which has received less attention from the CPU. Is it good for performance? Is it good for throughput? Is it good for latency? Is it good for real timeliness? Is it good for throughput? Is it good for power? It's certainly fair, right? It's trying to keep everyone sort of equally happy. But what about other dimensions? Okay, let's talk about it. Ability to meet real-time deadlines. Would it do that?
No guarantee.
Why not?
Because it's not taken into account what constructing the team.
Yeah, so what might happen is that there's one task which is critical, rest tasks don't care, but they're all going to be advanced at an equal rate. Okay, so it doesn't do that. Throughput.
It doesn't know if tasks depend on other tasks, or does it?
No, all it knows is tasks are sitting in this thing, how much time they've consumed. Just work on that. So throughput would be fine if you are thinking from the perspective of the system. If there's something to run, it will run it. Okay, so that it would be fine. What about power? So the issue which comes up here is the following. This scheduling is done for each core separately, right? So what's happening is I have a octa-core Samsung phone on each CPU. So beforehand, at a slower pace, I decided this task is going to this processor core, but different task is on a different processor core. So we kind of partition our tasks or threads onto these cores, and then on each core, I'm running this kind of stuff. Okay. Now tell me what are the advantages, disadvantages, something like this.
I'm not sure if I understand. So if I have a program that's made to run on multiple cores, can it still run on multiple cores with this scheduling?
No, so first, so remember, unless you are manually intervening, your program consists of a bunch of threads. And the OS decides these threads go to processor core 1, these threads go to processor core 2, these threads go to processor core 3, and so on and so forth. And it's doing that for all the programs, and it does it based upon whatever that governor it had, the policy it decided. And once assigned, this is changed less frequently, and like there has to be some significant change to revisit this decision. And then within each core, this kind of scheduling is being done. Okay, so within each core, it is basically keeping an account on what is happening and it does that. So what you may have the possibility is that on this core, no one is doing anything. The other core is heavily loaded at the time. But until you revisit that decision, because, and we talked about earlier that revisiting that decision means I have to move the thread from this core to the other core, so there is some state overhead associated with that. So scheduling suboptimalities can come in the sense I may have a core up, but I may not be able to use it because the tasks on it are waiting for I/O. Okay. On the other hand, I may have a core, different core, which is overloaded because the tasks there are perhaps CPU bound and all. And if it starts happening, the decision will be revisited because the OS will see that this core is too loaded, this core is not. It's probably going to shuffle things around. But until such time, these things will keep happening, and you don't want that shuffling to be done kind of much too frequently either. So from a power perspective, this is potentially kind of a bad deal because you may have lightly loaded cores up because remember they're still consuming leakage power and stuff like that. There's overhead of keeping the core up. So it would be good overall for health of the system if you could either shut down cores or scale the cores accordingly. Okay, so one of the things that people have therefore begun to do, including those of you who are from Professor Kaiser's group, a lot of work in your group, on modifying the CFS scheduler to account for power as well. Okay, so specifically, sort of you also take into account what the power characteristics of these tasks are and account for them somehow. Again, these are early days of kind of messing with power and scheduling in Linux, so kind of barring these ad hoc work, I think there's no definitive thing out there, but it's an area which is getting a lot of attention, particularly with the emergence of these big dot little type cores and all, where power issue becomes extremely important. So, energy aware scheduling on multi-core systems, a topic which people are exploring effectively. A lot of it is kind of still heuristics, gut feeling driven, those kind of things and all. Limitations also. So, for example, let's say I have this kind of system, 2 sockets, each with 4 cores. Frequency and voltage can only be controlled at the socket level. So I could have shut down an entire core and then consolidate everything on the core 1. Bad throughput. Why do you think bad throughput? Let's say I need only 4 cores. So I have this solution and this solution. All 4 into one socket, 2 on each socket. Claim is this is bad throughput. This is good throughput. This is good energy because the whole socket is shut down. This is bad for energy because I'm keeping 2 sockets up. So the energy part is sort of obvious. I'm keeping 2 sockets up with all the overhead and all. Why is this bad throughput?
Because if you do the second case, it's better throughput because you have cache on each core.
Okay, so cache is, I have an effectively larger cache, for example. Okay, what else? I/O. Okay, what else? DRAM access. Can kind of go to different banks in parallel. Okay, so essentially you have more resources that come at your disposal, which can be the same thing. So these are the kind of trade-offs that one would have to make, the scheduler will have to make to effectively use these things. And again, like I said, very early days, this thing, the schedulers that are out there are actually pretty primitive when it comes to exploiting these capabilities. When to idle thing and all. And confounding is the fact that it's not as if you have arbitrary control over what performance level you can have for these cores. Okay, there is some level of sharing that cores have within a socket. So, all of the story thus far focused on CPU only, but of course the same concepts of idle state management and performance state management apply to I/O devices as well. And in fact, more and more, the expectation is that it's the I/O devices or peripherals whose power management is going to be far more important than the CPU. The CPU is but a tiny part of these systems. So, just like we have the CPU FREC and the CPU idle framework, we also have a device runtime power management APIs. It's an API which allows device drivers and kind of controlling different parts of the system to go into different types of low power state in a systematic fashion. So we have a dev FREC system, which basically is the I/O device frequency scaling, and then we also have an associated framework where you can shut off clocks to specific devices as they are going to speed. So voltage frequency scaling independently of the different I/O devices is what is supported by this framework. And then there is a clock framework. What it does is that there is a system clock tree where so your system may have many different clocks. By clocks, I mean a couple of different things. Clock sources, so like there might be many different crystals, oscillators, and then from each one of those clock sources, there may be different clocks derived by using PLLs and all. So like, for example, from the same crystal, I may have a clock which is driving the CPU, a different clock which is driving the USB. And if I decided that the USB is being shut off, I can shut off that part of the clock. So what the clock framework does is it allows clocks to be shut down and thereby essentially doing software-based clock gating, which is you are shutting off parts of the subsystem by shutting off clocks to them. And the way what this framework does is it essentially gives device drivers a mechanism to state their interest in keeping a clock up. So essentially this is what happens. When a device is activated, it needs a clock, it needs a particular clock. It goes to that clock data structure and says, I'm using this clock. A different device which is using the same clock is going to do the same thing. And what the OS does is it keeps track on how many users are there for a particular clock, and if the count of users goes to 0, it knows that it can shut off that clock. Okay, so that's all that happens in this particular framework. It's keeping a reference count of how many users are there for a clock, and then shuts things down. Okay, and this is essentially kind of a software-based approach to clock gating that is happening. Back to this, so other aspects of this power management are then supported through the ACPI. So the ACPI again is sort of a low-level software that the board manufacturer provides, which the OS hooks up to. So there they implement all these different states of devices and also just like we have C state and P state for CPU, there exists similar states for every device, and the board vendor provides access to it. Okay, and then the office uses it, and there are calls there to interrogate. So like you can identify what all states do you have for a device, and the OS is customizing to that. So suspend, resume, changing the frequencies, and so on and so forth. Okay, so on future platforms, things are getting more complicated. So if you look at, like, again, Raspberry Pi or BeagleBone Black, two examples of good platforms out there, these guys, unlike the Intel systems and all, where you have, in case of Intel systems, you have like processor, you have a memory controller, these are all kind of separate things scattered all over the board and all. In case of these things, these are single system on chips, very integrated. Same thing with mobile phones and all also. So what is happening is that there is, and these are applications that are extremely energy intensive. So what's happening is kind of there's a tension in part, which is chip vendors are putting a lot of power management in hardware. Okay, so all this voltage scaling and stuff like that, kind of part of the thought is that instead of leaving it to the OS, let the chip do it. Okay, partly because they can do it better, but partly also oftentimes they need to, because like for example thermal reasons and stuff like that also dictate decisions they could perhaps be better than in hardware. So some of the responsibility for this perhaps is being grabbed away from the OS, and this goes back to this question of where is it best done. Okay, I think we might see more and more hardware playing a role of this thing. The other thing is that the power states become a lot more complicated to understand, because it's a single chip with, if you try to read like the power management states of a chip we have on Mbed or BeagleBone, these are much more complicated things, because not only there is a processor core, which is just a part of the chip, but there is all these other stuff which is sort of sitting on the same chip. So getting an overall power management picture is less clear. And I guess the sheer thing is there's a lot of diversity. So right now, this is kind of a challenge for an OS like Linux. It seeks to cater to all these different devices to have a framework which is general enough and yet customizable to all these variety of platforms. So what you would see is that a lot of these power management features and all are not yet available on devices like Raspberry Pi and all, okay, because there's still a lot of work which remains to be done to make that happen. Let's see. Okay. So another missing piece in all of this is how do we know how much power is being consumed? And that also, there's a fair bit of support towards that also. There are tools people have developed and all, for example. So there's one tool which Intel supports and kind of they're called PowerTop. And what PowerTop does is it keeps track of the state of the processor, whether it's which state it is in, how much power it is consuming and all, and then it exposes that. So it basically gives you a listing of all the processes, how much they have each thread, how much they have consumed, how many times they went in and out of different states, and so on and so forth. It's available on any CPU, any processor framework which implements the CPU idle framework. And using this, people find like energy bugs and things like that. There are alternative things also out there. So, for example, if you develop for iOS, the framework provides you kind of estimation of power in all of your codes. You can kind of see how much power different parts of your function were consuming. There are similar things floating around for Android also. So getting insight into the power consumption is important, and PowerTop kind of does that. So this is just kind of print out. So what all of this then boils down to is how do we go around implementing power management? So let's say typical like you just making a product, you decided on a board and all, you're going to use a processor, you're making your own board, you have to now decide you want to run Linux on it and have power management. So you'll have to provide the necessary driver support for the frequency control, the CPU flex system. You'll have to provide support for the CPU idle system. You'll have to provide support for the clock management system, and then also the whole board suspend to RAM or suspend to drive if you have that. You may want to write your own governors for the CPU flex and CPU idle system. So these are user space things. And then after all of that, then you also would have to take measures about optimizing your application, so not running unnecessary stuff and then sitting down and seeing where is the power going and kind of optimizing things based upon that. So the task becomes harder in embedded systems because oftentimes we design our own boards. Okay, we take a chip, we design our own board, and now porting Linux to a board like this involves, if you want to be power efficient, it involves writing all this other stuff also. The other alternative is you don't design your own board, you kind of, or whatever, make your board essentially identical to something like Raspberry Pi or BeagleBone so that you can leverage what is happening on that side of things. Not always easy. How many of you know that Raspberry Pi is actually not open source? It's associated with being open, right? I mean, that's how kind of it is. But the chip which is used on it, it's a Broadcom chip, and Broadcom is one of those companies which tends to be extremely secretive about its data sheets. So there are no data sheets. They have dribbled out information in bits and pieces. So there's some stuff out there. People reverse engineer. They changed, the new Raspberry Pi has a different chip, but there are no data sheets on it and all. So actually, for a platform like this, writing power management, part of the reason it's so behind is writing power management is not easy. BeagleBone, on the other hand, uses a TI chip, a lot more open. So you are at the mercy of the chip vendor. Okay, Intel tends to be much more open. Qualcomm tends to be very close. So these companies have different approaches towards this.
What's the Arduino one?
What's the Arduino one? Anyone knows? What's the Arduino one? Yeah. It's totally open. Atmel again is one of those very nice companies. So, but Arduino now also actually has generalized. There are ARM-based Arduinos also. So I don't know what chips they use, but my guess is Arduino has always had a strong bias in favor of using totally open stuff. So I suspect they are open. But Raspberry Pi was a bit of a. I mean, I always assumed they were open and all. That's the whole public image was kind of like that, but it was kind of interesting that large parts, I mean, yeah, Broadcom has dribbled out binaries and all, and like you can write stuff, but a lot of stuff is just is not known, and it's very hard to do these things. Okay, so on the other hand, let's say take like I said, BeagleBone Black, which we used it. It's totally open to the extent that they actually have the entire board design on a GitHub-like website, which is meant for board design. So you can actually literally take that design and put it as part of your board and build the rest of your board around it. So it's pretty cool that way. And the chip is totally open and all, but one sad component to the whole thing, that chip is dead in the sense that TI pulled out of the mobile market, so there's no future. So if you're a product designer, you're not going to base your chip around something which has no future. So these are kind of all tricky decisions at this stage. So for custom products, it tends to be kind of a tricky thing at this stage, in the sense there is a reason a lot of like companies like Apple and all make their own system of chips and all, because they have entire control over it. So anyway, that's part of the power management story. You have to implement the whole clocking structure, implement the handlers for suspenders, all those kind of things, a lot of board specific stuff, and then you would be able to leverage a lot of these other things that are already there. So essentially there's this thin layer below the Linux framework which you will have to write, which is essentially the drivers for your specific board for it to effectively use these power management capabilities, but the rest is there. So to summarize, and I'm going to end early as a result, so Linux kernel has pretty nice support for power management, nice in the sense that it's very open. You can port it, all the details are there. It is not very elegant in one regard, which is it has a separation of runtime and system-wide power management and all. There is no logical reason. But having said that, there's the information about Windows and Mac and other such operating systems is so little that there's no comparison point. I/O device power management frameworks are also there, but far less mature. Some of the things that currently exist, like hibernation and all, are basically effectively dead. They are likely going to disappear. Scheduling is going to become more energy aware. That's kind of a trend. And then these complicated things like multiple cores and all are also kind of coming into play. And there are other complications that come into play. So to give you another example, so we talked about multiple cores. Those cores could be put to sleep. Now, a very common way of maintaining time in Linux is to make use of a register which Intel popularized, which basically counts how many clock cycles have run since the system powered up. Now, that's very nice because it gives you a counter which is running at the frequency of the CPU, which is gigahertz. So you have a nanosecond resolution timer. What do you see is the problem with that? With this whole power management story that I have described. So it's used as a high resolution timer. You can see, and you can see how many cycles have been executed since the system started running.
So first of all, does it need to be that accurate down to a nanosecond? Does it need to be that accurate down to a nanosecond?
Yeah. Yeah, sure, why not?
But like the clock ticking also takes energy.
No, but the CPU is running at that in gigahertz anyway, so it's not like I'm spending any extra energy because of that.
Will it overflow?
Yeah, but let's say you take care of it. That's not the issue. So I'm relying on this value to basically keep track of very fine-grained time. That's kind of an assertion. That's how if you look for high-resolution timer, you will see this description. And I think there's a particular name for this counter, which, I don't know, do you know? No? Okay. But what do you think with power management? So the assertion I'm making is with power management, it actually messes up with my timing maintenance. Okay, so I'm basically trying to see if you guys can see why would it cause problems with with time management.
Is it related to the clock drifting?
Now, that would have to do with the crystal, right? Nothing to do with that. So let's say I'm an app or program running on a core, and whenever I need the time, I go to this register and I take the reading. It's telling me, and by the way, this register they tend to be 64 bits, so they don't overflow easily. Okay, so I take the reading and I multiply it by the CPU frequency, and I say, voila, that's the time I've been up. And then I'm trying to measure the time taken by a piece of code, so I do it before the code, I do it after the code, and I say, wow, this is the time I took. My claim is that that's very misleading.
Because when you do power management, the frequencies changes also.
Okay, so frequency can change. So that's the problem, right? I mean, frequency can change. In fact, worse yet, frequency may be changed by some hardware governor. I may not even have control over that. Okay, so I cannot simply multiply it by some constant number. I have to know when the frequency changed to do it. In fact, it can create significant problems with benchmarking, actually, because what happens with benchmarking and all is that the initial stage when the program is being loaded up and all, the load is higher, so the CPU frequency is higher. So for the same time passage, a lot more clock ticks happen. Okay, so that's one issue.
But I have a question regarding this one. CPU frequency changes, but the time of frequency does it also change?
Yeah, because all it is doing is counting how many clock ticks have spanned since.
But you can keep track what the frequency changes so that you can multiply this part by this amount of frequency.
It's not easy. Part of the reason, if all frequency changes were initiated by software, you could, although it would be a lot of state to maintain. Ignoring that problem, the issue also is oftentimes the frequency change happens by hardware. It doesn't even drift up to the OS, because what happens is that overriding everything that the OS is doing are thermal considerations. So the hardware's first rule of hardware, protect thyself, right? I mean, so it's going to make sure that the chip doesn't burn. So if the temperature starts rising up, it is going to lower the frequency irrespective of what the OS might be telling it. Okay, so not everything is under the control of hardware, control of the operating system. There is hardware override to that. Okay, which is why, I mean, you get these things like, right, too hot shuts down, right? Okay, so that's hardware kicking in. Okay, so you're right. So that's one point. There's closely related. What do you think about shutdown? What impact would that have? Similar issue, right? I mean, at some time T1, I took the reading of this counter. Sometime T2, I again took the reading of this counter, but in between the processor was idle and therefore was shut down by the power management scheme. And I'm looking at T1 to T2 passage of time. Now it depends upon how am I using it. If I'm using it purely as how much execution time I had on the CPU, it's fine. But if I was using it for purposes of measuring the passage of time, passage of real time, it's going to be incorrect information. So what do you think the solution is to problems like these? Intel is solving it. So what would be the solution?
Can they have a separate clock just for this register?
Yeah, kind of. So essentially, now what they're doing is on these multi-core chips, they keep one part which is always up and running just for maintaining this counter. Okay, so that you don't run. So two things. Number one, it is always up, and number two, it is fixed frequency. Okay, so obvious answer. The point I guess I'm trying to make is there are all these weird interactions that end up happening between power management and other aspects of the system. So they, like when multi-cores got introduced and all, suddenly and power management became aggressive, all these problems came to light. So gradually now they are being addressed. Okay, so it's a complicated story, and these are complicated systems with lots of moving parts, oftentimes unanticipated effects. Okay, so we're going to stop here and going to pick up a different topic on Thursday.